So we need to store all of these raster values that go into our raster GIS layers. And most are stored in something that we call a binary format. So with a binary format, each value has a choice of being either 0 or 1. That would be called a bit. And then 8 of these bits together is called a byte. So in this example here, 8 zeros together would be the lowest value. That would be a value of 0. And all values of 1 here would be the highest value. That would be a value of 255. So with values ranging between 0 and 255, there are 256 possible values in each byte. And that happens to be 2 to the 8th because each one of these 8 places here is kind of like a placeholder. If we go to 2-byte data, now we have 8-byte data next to 8-byte data, and we can list those all together. Those can vary anywhere from 0, once again, 16 different zeros in a row, to any combination of 0 ones here until we finally get up to 111, 16 of these ones, which would give us 65,566 different combinations, which happens to be what 2 to the 16th is equal to. So we can always just raise this by 8 more. If we want to see what 3 bytes would be, we would just say 2 to the 24th, and that would tell us what how many storage spaces we would have with 3-byte data. So each of these pixels uses a byte to represent it, and if we need more space, we can add additional bytes. So once again, 8-bit pixels or 1 byte is going to be 0 to 255. 2-byte data, 0 to 65,565, and 3-byte data, that's the same as that should be 2 to the 24th, and that would be 16,700,000 plus values that it could possibly have. So the other thing that can really influence how much storage we need in order to store these raster GIS layers is whether or not it's a integer or floating point. Because with floating point, we're going to have to store a lot of decimals after the decimal point and maybe the power of that. So really it adds a lot. With floating point, we need 32-bit data, which would be 4 bytes. And that really increases the amount of storage that we need for such data. So each of these data is typically, if it's 1-byte data, each one of these can have values from 0 to 256, but sometimes we have multiple layers over the same area. One example of this would be Landsat imagery or any sort of satellite imagery, where we measure the same area at different bands, and these different bands might represent a different part of the electromagnetic spectrum, such as what was collected from the red portion of the electromagnetic spectrum, the green portion, the blue portion, and so forth. So we can have multi-band rasters. Each one of these bands represents, for example, a different portion of the electromagnetic spectrum, and we could store those together as a multi-band stack, which just means they all cover the same area, they were taken at the same time, so we're going to store those all together. And this gives us some real options. So for example, all 7 of these are black and white images where we're using shades of gray between 0 and 255 in order to represent this area around Crater Lake. So in each one of these images, we're just using a grayscale, and we're using 256 different shades of gray in order to represent that area. But if we have a multi-band stack, we can combine those by not assigning those 0 to 255 values to shades of gray, but instead assign them to individual colors such as red, green, and blue. And when we mix red, green, and blue, those 3 different 8-bit colors, if we use 0 to 255, then suddenly we have 16.7 million different colors that we can have in a remote sensing or a satellite image or a UAS image. So a raster band can be assigned to any of those 3 colors, and some ones we typically use, this would be something that's called a natural color, where what was measured in the red portion of the electromagnetic spectrum is assigned for display to the color red, what was measured in the green portion is assigned for display to the color green, and what was measured in the blue portion is assigned to the color blue. However, this is a common thing that we show because this highlights where healthy green vegetation is. We could assign what was measured in the near infrared portion of the electromagnetic spectrum to the color red for display. We could take what was measured in the green portion of the spectrum and assign that to red, and take what was measured from the blue and assign it to blue. And this would give us what's called a false color composite image. And here's another example here where we can even take bands that aren't visible to the eye, such as this band 7, and assign it to one of the visible colors, such as red. This one's assigned to green, and once again, that one's assigned to blue. So one other thing to talk about with storing this raster data is how we can compress it, because these things can get very large. And there's two different kind of ways we can compress things. One is called reversible, because we can go back to what the original data was. And the other is called irreversible, or sometimes it's called lossy data, because we can never get back to what it was before we compressed it. So compression here means that if you don't save the original, you can never get back to what you started with. Let's start with this reversible one here. If these are our pixel values in order, going 0, 1, 1, 1, 1, 1, 3, 3, 3, 3, we can see that sometimes we get a lot of repetition in our data. And this might be something if we're looking at land use data, where maybe a field of corn is right next to another pixel representing a field of corn, next to another pixel representing a field of corn, and so forth. So we get a lot of these clustered together. One way to store that data is like this. We say we have a value of 0 as our first pixel, and we have one pixel that was 0. But then after that, we have a value of 1, and that's good for the next 5 pixels. So we just put a 5 after that. And then we have a value of 3, and that 3 is good for the next 6 pixels. 1, 2, 3, 4, 5, 6. Then we have a value of 5, and that 5 is also good for the next 6 pixels. And we continue on like that. 7 and 1 are only good for 1 pixel. So instead of storing this entire string here, we can just store these numbers here, and we can actually save some space as we store that data. The irreversible one, in this case, just truncates off everything after the decimal point. So we had a value of 1.2, 3.6, 4.2, and 9.8. We would just do a lossy compression of that and go to 1, 3, 4, and 9. Even though this was 9.8 and much closer to 10, we're just going to store that as 9 because this is a truncation. You can just kind of think of it cutting off the end of that. And you can imagine if someone gave you this data here, there would be no way that you could get back to this data here, right? You would have to find the original data if you wanted to know what those decimal values were and needed that sort of precision. So one way to think about raster data is that we kind of have data rasters and picture rasters. And so sometimes rasters can represent things like elevation or aerial imagery or land use or where roads are, and those would be examples of data rasters. They store values, and those represent measurements that we are able to analyze, whether there's a digital elevation model, the actual elevation at a certain location, or what type of road is located at a certain location. But other ones are picture rasters. They're just basically taking a picture or a scan of a map, and these are typically used as base maps or topo sheets, or in this case topo sheets, in this case a tile for something like ArcGIS Online as a base map. And we're just kind of using that as a backdrop for the information or data that we want to put on top of it.